Hello, my name is Bernhard Krage and I'm presenting the paper Inductive Sequentialization of Asynchronous Programs, which is joint work with Konstantin Enniar, Tom Hensinger, Suha Mutlu-Ergil, and Shaz Kadir. Distributed systems are an integral part of today's computing landscape, and we heavily depend on them, not last to run this virtual PLDI. To ensure the reliability of distributed systems, many recent works have demonstrated the feasibility of formal proofs of correctness, even down to real implementations. The core verification technique centers around the notion of inductive invariance. An inductive invariant is a property that contains the initial states of the system, it is disjoint from the dark corner of unsafe states, and most importantly, it is closed under the transition relation of the system. Unfortunately, devising inductive invariants for concurrent programs is notoriously difficult, error-prone, and time-consuming, even for experts. This is due to the sheer number of interleavings of a concurrent program, all of which have to be accounted for in a formal proof. For example, proving the correctness of the infamous Paxos algorithm requires the invention of an inductive invariant that captures increasingly complicated properties of concurrent interleavings. Intuitively, this is the case because the protocol operates in a sequence of rounds that can arbitrarily overlap. In this work, we present a technique that significantly simplifies formal proofs. Our technique only requires the simple part of the invariant and eliminates all the complicated part that is hard to invent. Our key idea is to prove just a single execution of the concurrent program, one that has a simple interleaving and avoids corner cases. For example, where all rounds execute one after another, and within each round, the phases are strictly ordered. Then we use simple arguments to guarantee that the sequential reduction in fact covers all other concurrent interleavings. In summary, our main contribution is a new proof rule called inductive sequentialization, which turns complicated reasoning about concurrent programs into simple reasoning about sequential programs. We integrated inductive sequentialization into a refinement methodology that allows us to prove fine-grained implementations. Finally, we implemented our methodology and demonstrated its applicability and usefulness on a number of challenging case studies. In this talk, I'm going to explain our technique on a simple toy example called broadcast consensus. In this example, each node starts out with an arbitrary local value, like 2, 5, and 8 on my slide. The goal of the protocol is to get all of these nodes to agree on a common value. And they do so by running 2 concurrent threads per node, denoted by a purple and a blue box. The purple thread runs the procedure broadcast, which sends the local value of a node to all of the others. So node 2 broadcasts value 2 to all other nodes, node 5 broadcasts value 5 to all other nodes, and node 8 broadcasts its value 8 to all of the other nodes. Now the blue collect thread collects incoming messages. So if we look at node 2, it receives 2, 5, and 8, and the algorithm is to take the maximum incoming value as the local decision. So node 2 decides on value 8. Similarly, node 5 receives 2, 5, and 8, and decides on value 8. And finally, also node 8 receives 2, 5, and 8, and decides on value 8. Unfortunately, even this simple example has many different asynchronous executions, like the one I'm showing now on the slide. Let's pause for a second and observe that in such an execution, at any instant in time, some subset of send operations already happened, some subset of the sent messages was already received, and the intermediate decision that each node currently has is not yet final. Our goal with inductive sequentialization is to avoid reasoning about all of these asynchronous executions explicitly. Our work builds upon the powerful notion of mover types. A mover type characterizes the commutativity properties of a primitive atomic operation. For example, the send operation is a so-called left mover. Consider an execution where send A is followed by send B, where here I'm using clouds to represent the intermediate network state. In this execution, send B can be moved to the left, and we obtain the execution send B, send A. That still results in the same end state where A and B are in the network. Similarly, send B can be moved to the left of receive A, because after sending B, A can still be received, and we end up with only B in the network. And similarly, receive is a so-called right mover, and we already did half of the justification, because moving a receive to the right of a send is equivalent to moving the send to the left. And also, receive commutes to the right of other receives. Receive A and followed by receive B can be commuted to receive B followed by receive A. However, it is not the case that send is a right mover, nor that receive is a left mover, because a matching pair of send and receives cannot be commuted. Now, other than send and receive, our broadcast consensus protocol uses asynchronous thread creation, which is a left mover, and thread local reads and writes to memory, which are both left and right movers. Now, the point of establishing mover types is to apply a result that is called Lipton's reduction, which says that if a thread, the black one in my example, executes a sequence of right movers followed by a sequence of left movers, then no matter if it could really be interrupted by other threads, we can always consider the black thread to execute atomically, because we can commute its actions such that they appear in one consecutive block, denoted also by a brace around the block. And now by looking at our broadcast consensus algorithm, we see that in fact each of the procedures satisfies this requirement, and so we can convert each of the procedures to coarser-grained atomic actions. Concretely, the broadcast action is now one that atomically, in one shot, sends all the local values of a node to the others, and the collect operation blocks until it can receive all the incoming messages at once and make a final decision. Now that our program consists of coarse-grained atomic actions, there are two important observations. First, these actions again have mover types. Concretely, action broadcast is a left mover and action collect is a right mover. And second, while this program has less interleavings, it is still concurrent and has many interleavings between the broadcast and collect operations. Now, our contribution with inductive sequentialization is to go all the way to a sequential program. Concretely, the one I'm showing on the right. This program executes the broadcast operations first in the order from 1 to n, and then it executes all the collect operations, again in the fixed order from 1 to n. Now, as an illustration, consider that n is equal to 3. Then this means that this program really only exhibits a single sequential execution, where broadcast 1, 2, and 3 happen, and then collect 1, 2, and 3 happen. So how can inductive sequentialization justify that the single sequential execution in fact captures all other concurrent executions? The answer is to further exploit mover types. In our sequentialization, broadcast 1 should be the first operation. And since broadcast is a left mover, it can always be moved to the left at the beginning of the execution. And continuing in this fashion, we can step by step increase a sequential prefix. Unfortunately, in any non-trivial program we will get stuck, because not all operations are left movers. In our example, this happens because collect is not a left mover with respect to broadcast operations. Now, our crucial insight is that this is not a problem, because in the sequentialization, all the broadcast operations are already sequentialized, and so the collect operation only has to be moved to the left of other collect operations. To solve this problem, inductive sequentialization supports abstraction. Consider, for example, the abstraction collect apps, which asserts that when the collect operation executes, there are no other broadcast operations anymore. Here, I'm using the omega symbol to denote the set of pending threads. Now, this abstraction is of course not valid in arbitrary concurrent executions, but it is valid in our sequentialization. And most importantly, collect apps is now a left mover. And so by using collect apps, we can continue our sequentialization, and eventually we will end up with the complete sequentialization. Now, inductive sequentialization is a proof rule in the style of deductive verification. It proves correctness for an unbounded number of processes and does not really enumerate or rewrite any executions. What it really does is it takes an input concurrent program and rewrites it into an output sequential program. To do so, the central proof artifact that has to be specified by the programmer is a so-called sequential invariant action. This invariant action is similar in spirit to an inductive invariant. However, instead of capturing all the concurrent intermediate states, it only captures the partial sequentializations that we saw on the previous slide. So it really has to satisfy three conditions. First of all, it has to represent the empty sequentialization that we start with. Second, it has to be inductive, but only with respect to one action at a time. So really the sequentialization order that we follow is specified as part of the invariant action. And potentially, inductive sequentialization takes left-moving abstractions that are used during this induction step. And finally, the invariant action also represents the complete sequentialization that we take as an output of the transformation. So in summary, inductive sequentialization is a tight combination of induction, commutativity reasoning, and abstraction that derives its power from this tight interaction. In our paper, we give a detailed formalization and correctness proof. We implemented inductive sequentialization inside CIVL, a refinement-based verifier for concurrent programs that is built on top of Boogie, a verifier for sequential programs. We used our implementation to demonstrate the effectiveness and broad applicability of inductive sequentialization by applying it to the case studies shown at the bottom of the slide. Across these examples, we see many synchronization mechanisms, network topologies, channel types, and correctness specifications. Overall, our case studies showed that inductive sequentialization significantly simplifies proof construction by appealing to sequential intuition. Our verifier is highly automated. It automatically discharges all the verification conditions that are induced by inductive sequentialization. It is also very fast. Verifying all of our examples is a matter of seconds. And finally, it is suitable for interactive development, where failed proof attempts are attributed to small checks that helps systematic proof construction and debugging. In CIVL, we generally advocate the construction of proofs across multiple layers of refinement, where a low-level implementation is gradually abstracted up to a high-level specification, or alternatively, a high-level specification is gradually refined down to a low-level implementation. In this layer proof, each step corresponds to a small, simplifying program transformation. This decomposition makes proofs both more manageable and reusable. In the case studies for our paper, we verified all of our examples as follows. On the bottom layer, we started out with low-level implementations that only use primitive atomic operations, like send and receive, and memory read and write. Using the existing transformations in CIVL, like Lipton's reduction, we abstracted these low-level procedures to more coarse-grained atomic event handlers. Crucially, this first step does not yet require any invariant that is really related to the correctness mechanism of the protocol. However, it enables to apply inductive sequentialization in a subsequent step. And since inductive sequentialization is guided by a single sequential execution order, the actual proof of the protocol mechanism is greatly simplified. In our paper, we provide a detailed discussion of this methodology to verify Paxos. In particular, we show the simplification afforded by our sequential invariants compared to standard concurrency-aware inductive invariants. The takeaway message here is that the intuition from a single representative execution can actually be lifted to a formal correctness proof, and inductive sequentialization provides the formal machinery to do so. To conclude my talk, I'd like to point out one core distinguishing design feature of CIVL. In CIVL, each refinement layer actually remains a structured program, meaning a program with procedures, imperative control flow, and both structured and asynchronous concurrency. This is in contrast to other refinement-based verifiers, like TLA Plus or Event B, which operate on the representation of concurrent programs as flat transition relations. In our view, using programs has the advantage of naturally bridging the gap to real implementations, and we do not lose the structure inherently present in the program syntax. The foundation for building a verifier based on the structured program representation is described in an upcoming CAF paper. Thank you very much for listening. I'm looking forward to an interesting Q&A, and even more so, I'm looking forward to individual discussions. Please get in touch with me using the email address below.